Okay, so writing a tiny compiler in Swift, aka how I spent the last week, aka why I needed a lot of coffee this morning. So if you want to follow along, all of the code is on GitHub in a slightly more polished form than in the talk. So I built a programming language that I have called Sipquick, and I built a compiler and test harness for it in Swift. So what's a tiny compiler look like? 310 lines of code. I'd say that's pretty tiny. I didn't go through and count for the Swift compiler, but I'd take a guess it's probably over 100,000. So pretty tiny by comparison. So why did I write a compiler? Yes, I was nerd sniped into it. This is how I get into many of my projects. But really, compilers are something that we interact with every day as developers. So number one, I want a better idea of how compilers work. What happens when I run Swift-C or when I run Clang. So it's also a thing that people know how to do pretty well at this point. There are lots of compilers. You can Google, like, how do I do X in a compiler, and you'll get something a bit better than Stack Overflow answers. You'll get blog posts and books and rants on Twitter. It's something that's doable in any language. It's a project that takes a text file and transforms it kind of into another text file. So you can do that however you want to do. And I've never written a compiler before. And now I have, so I can put on my resume, compiler engineer. So what is a compiler? It's a really simple function. It's a thing that takes in a string, what we would call a source file, and prints out an executable. That's really simple, right? It fits on a single line right there. I've defined a compiler. We can all go home. So yeah, it transforms source into an executable. So it transforms a program written in one language, usually something that we can read and understand and write and reason about, into another language, a language that is meant for machines to read and understand and reason about and execute. So you may be thinking, okay, so great, you wrote a compiler. Sam, how do I write a compiler? Well, there are a bunch of well-known steps. You parse source code, you lex it, you do what's called semantic analysis. So you say, okay, these tokens that I have, what do they mean? So like in Swift, what does the word class mean? It means something very different than when reading marks. I can tell you that. You optimize it, so you say, well, Sam, you wrote some really slow code. I know we're going to have a talk about Swift performance later. So optimizing is, you wrote this code, great, I'm a machine, I'm smarter than you, I'm going to turn this into faster code. Optimize. And then you generate some more code. You generate machine code. So compilers, by their nature, are highly functional. We heard a bit about functional programming earlier. So I built a language called Sipquick. It's a very loud, noisy bird in a book that I like. And it fits in with Swift. It has an S. It's a bird. I'm really just trying to hit that hashtag brand engagement audience here. So it's a very small language that I invented for the purpose of this talk, because if I tried to write a compiler for another programming language, I'd actually have to implement a lot more things and not be able to decide how it would work to make things as convenient for me as possible. And I'm lazy, so I wanted to make things as easy as possible. So it's a language built on S expressions. So this is just like Lisp. Everything goes in parentheses, and you use your editor to, there's one person who's written Lisp here, great. So, you have to go into your editor and hope it underlines the matching parentheses so you can get things to compile. It's a dynamic language, so there are no types at compile time. The compiler doesn't know what a type is. And it's functional-ish. So it does have side effects in the language, but by its nature, every function takes in arguments and it returns something. So this would be how you write hello world in Sipquick. Def is the keyword to define a function. It takes two arguments, hello, and the function is named hello. It takes an argument named name, and then it concatenates a string. We call it, we print it out. So, doing this, step one was build a parser. I lifted most of the code from a Try-Swift Tokyo talk about building a parser. Lifted a lot of the ideas from it. It's a parser combinator, so there are fun things like monads and all that in there. I don't like fancy operators, so I changed it around into something that I could read at the time I wrote it. I'm not so sure it's as readable to me now. So this is kind of the main parsing. This is ignoring all of the machinery to set up the parser and some of the definitions for what an S expression is. But the basic idea is we parse in a bunch of S expressions, and then we say either, there's this 5 trailing slashes at the end or at the end of the file, and that's it. And so we end up with an array of S expressions. So there are a whole bunch of generics there. The compiler doesn't really like that. But we transform the strings that we get, the tokens, into S expressions. So this is the one functional Swifty thing I will talk about, I promise. So inline, whenever we parse something, I transform it into something that makes sense for the AST, abstract syntax tree. Inline, I say, oh, hey, these empty parentheses here, well, that's an empty S expression. Inline, and that keeps things really simple. I don't have to reason about what do these strings mean in different positions. It happens in that one parser.swift file. So there's this idea of semantic analysis. So we've parsed things out. We have tokens. But a lot of tokens in many languages have special meanings. How do you define a function? How do you call a function? How do you define variables? Things like that. Or keywords. Are there operators? How do things work between different lines? Stuff like that. So that's what semantic analysis is. It's taken this abstract syntax tree and basically collapsing it down into something the programming language knows about, which are expressions. So, we basically have a bunch of different, we have one initializer with a massive switch statement. Again, wrote this in the past week. I would not take this code as an example of production Swift. So we switch on what we find, and we turn these S expressions, the Lispy things into the sort of expression that the compiler can reason about. So is this expression, is its kind defining a variable, or defining a function, or calling a function? Stuff like that. So yeah, in most compilers, we'd say, okay, is this program correct? Is it well-formed? In a language like Swift, this would mean, do the types check out well? Are we calling this function with the right type of arguments, with the right number of arguments? Does this function even exist? This language does absolutely none of that. Another thing this compiler does not do is any sort of optimization. So optimizations are, ironically enough, one of the easiest things to do in a compiler. Because if you look at the sort of transformation it is, it's basically, ooh, that is not valid Swift syntax. Bad Sam. Oh, no, it is. So yeah, optimizations are basically saying, okay, I have expressions here, and I turn them into expressions there. And in most production strength compilers, you will have many optimization passes. This is where you do things like, oh, hey, is there unreachable code? Let's get rid of that. Is this like a pure function that's used twice? Well, we can, calculate the value once and use it in both places. I didn't do any of them. But it is a very important part of what compilers do, and it is a part of, the compiler writing process that people spend a lot of time on. Because think about it this way. If I spend 10 hours implementing an optimization that can make your code run 1% faster, well, there are a lot of you. Each one of you has a lot of users. 1% faster code equals, hundreds, thousands, millions of hours. And optimizing compilers are also a source of a lot of academic research. What sort of transformations can you make safely? All that stuff goes way over my head. So code generation. So this is where we say, okay, I understand what this program is. I understand as the compiler how this is supposed to work. But now I have to, output something that the computer can run. So we take our expressions and we transform them into some sort of executable. So what counts as an executable? Well, machine code. This is what something like Clang and LLVM do. Has anyone here ever used something like Babel? Babel.js? Okay, a few people. So that will compile, some form of JavaScript-y thing into another JavaScript-y thing. That's still compilation. So I think code generation is really, really hard. There's a great, the easiest way that people think of doing it is, okay, well, you just import LLVM, and you spew stuff into LLVM, and it has lots of optimizations and stuff in it, and it'll spew out really good machine code. That works great if you have something like C. Turns out LLVM was built for like C and C++ and Objective-C compiler writers. I was building a language that's very dynamic, untyped, where you don't know, is this a string, is this an integer, does this function exist? So, tried to fit it into LLVM. That didn't really work out well. So this is sort of the idealized how do modern compilers work. And all the LLVM magic happens at the end there. But I couldn't go that route, so I had to do things the hard way. I compile my Lispy thing to Ruby. It's a dynamic language. It has a robust standard library, so I don't have to write things like, oh, hey, how do I access the arguments passed to this program? How do I output something to the screen? I didn't have to do any of that. And I know Ruby and its syntax and its standard library probably more than is healthy for any developer to know anything about their programming language of choice. So yeah, code generation. Basically implemented as an extension on expressions. You say, okay, so I have an expression and I want it to be represented as Ruby. And this is another one of those turtles all the way down thing. It's recursive. You have expressions that contain other expressions. So think in terms of a function call. You have, ooh, that's no good. You have the top level function call, and then maybe the arguments themselves are other function calls or expressions.
This handles that, and you output Ruby code, which you can then run.
if you have a working Ruby version on your machine, and given that it's implemented in Swift, and I guess no longer you have to have a Mac to do that, but it comes by default on OS 10, and I didn't really feel like diving in enough to Bash to get it to compile to Bash. So this seemed like a safe middle ground. So yeah, the gist of how this works is we have expressions, and we literally just map the expressions to $0 dot as Ruby. Join them together with new lines, add a shebang at the top, and run chmod so the thing is actually executable, and we can run it. So how does this step sort of look like? We have a definition of, what is the nth Fibonacci number? And yes, Lisp is not the most expressive language. There are lots of parentheses. The prefix notation gets some getting used to. But it compiles to something that looks like vaguely friendly Ruby. And if you run it, it actually works. This is the entirety. I know you can't read that, and that's intentional, but that is the entirety of the code generation step. It fits into one file. I could probably fit it onto one screen if I made the font size like size 10. So very compact, very easy to do. Targeting Ruby made that really nice. It's basically switch on what kind of expression is it. And maybe pull out, okay, this is a function definition, these are the argument names, stuff like that. But other than that, it's really pretty simple once you've done semantic analysis, once you've done optimizations to say, okay, let's output to a target that sort of reads the same as the language we're working in. If I tried to make this compile to Swift or C, that would have been a bit more difficult, because then, well, okay, is this number an integer or a floating point number? Is this a string or a character? Stack allocated, heap allocated? So that's sort of the mismatch that you can get when trying to think in terms of what does a traditional compiler do? It really depends on what sort of language you're compiling to begin with. So yeah, using the compiler, you write I like the .spq extension. So you write a file, you call Sipquick that file. You can optionally say what file to output it to. Then you can call it like any normal executable. Pass in arguments, stuff like that. Okay, so testing a compiler. And yes, I wrote tests. I was thinking about not writing tests, and that voice in the back of my mind started yelling at me. So testing the compiler. I only wrote integration tests. So they basically compile a file, they run it, and they verify that the output is exactly what I expected. Only testing, this is how things should work. This is how a well-formed program should compile and run, not the other way around. And I wrote 0 unit tests. So this is what a test case looked like. It basically had the Sipquick on top, 5 slashes, name of the test case, the expected exit code, and the expected output to standard out. And this is, again, probably a bit hard to read, but this is the test runner. Has the idea of this is a test. You expect, it has a name, it has a script that you run, it has output that you expect, an exit code that you expect, and then you just run it and make sure that those things are equal. Again, figure out, okay, what's the path to the compiler? What's the path that has all the spec files? Find all of them, instantiate those test cases, run them all, and see if they all pass. This is the last one that I wrote today, just this morning. I tried to write FizzBuzz, had to fix a few bugs in the compiler to make it work, and had to spend a while wondering why things weren't working because I had mismatched parentheses, because everything actually only fits on one line, but it works. I wrote FizzBuzz in my own language, so next time I'm asked in an interview, can you write FizzBuzz for me? Pick a language. Do I have to implement the compiler for it too? Because I've got that down pat. So I know I'm running out of time now, but there are just some to-dos that I have to do for this compiler I want to quickly run through for y'all. I wrote bad Swift code, and things are structs that should be enums. There are no optimizations. So Ruby code isn't the fastest in the world, and I'm sure that my thing that compiles to Ruby is going to be even slower. So I can make that faster. You know, stuff like how functions work are less than ideal. There are no error messages. Things just fatal error if we don't produce a proper S expression. That makes figuring out why things are failing to compile really, really difficult. There are no semantic analysis errors, so you can define functions with the wrong number of arguments and you know, call functions with the wrong number of arguments, and you can define a function that, like define a variable that's actually a function. It's a mess. And it compiles to Ruby now, and it probably shouldn't. It would be really fun to explore compiling to machine code. There's more things to do. There's no proper standard library. I'm piggybacking off of Ruby's standard library right now. Comments don't work. And I know several friends who would yell at me for building a programming language that actually disallows commenting. There's no notion of lambdas, which is really weird if you think of a Lisp without lambdas. Also, a Lisp without lists. It just didn't feel right to me. So, you know, that's something I probably should do at some point. Expressions can only have like a single expression in them, so function bodies have to be purely functional right now. There's no way to, you know, let's say print a value and then call another function. Okay, quick lessons learned doing this. Number one was don't write a compiler for a conference talk. It's a lot of work. Yeah, writing a compiler is really, really hard. There's a reason that, you know, you specifically have compiler engineers as their job title. Testing a compiler is really necessary because I didn't write a single thing that worked right on the first try. String parsing in Swift is really hard. It's, you know, yes, being Unicode aware is great, but it also makes parsing like source files kind of difficult. Error messages are hard. Like, this seems kind of obvious, but it's really hard to report, why does this thing fail to parse? What's wrong with it? How do I say, oh, you're missing a closing parenthesis here? And the LLVM API, which I really wanted to use, is really meant for typed languages, where you can infer that this variable is an int32, or, you know, this function has this function signature. And implementing your own programming language is really fun and really rewarding. Like, you know, on my GitHub, I have a programming language. Again, I can go into a job interview, and if they ask me to whiteboard something, so do you want me to use Ruby or Swift or the language that I wrote? And yeah, real programming languages are much better than what I wrote in the past week. But they take a lot of time and a lot of effort and a lot of know-how. And so next time I want to complain about how Swift C fails to do something, I think I might understand a bit better why you know, these things are hard. So thank you.